In our next section, we're going to look at the content-based access control, which is the IP inspect feature, along with high availability, and see how it integrates with the HSRP feature in order to do active standby stateful failover between a pair of two routers. Now, additionally, we are going to later talk about the zone-based policy firewall and high availability, but we're going to come back to that after we talk about ASA failover first, because the configuration of the iOS zone firewall high availability is closer to the ASA's failover, and it makes a little bit more sense to look at how ASA does it first and then circle back around to iOS. Now, as I mentioned, essentially what this feature is, the CBAC HA, or the iOS firewall high availability, is the integration between the inspection engine and the HSRP feature, which is our hot standby router protocol, which is our first hop redundancy. Now, if you know any of the details about how HSRP works, then you can assume how CBAC is going to integrate with it, meaning that it only supports active standby failover, not active. Because with HSRP, only one router is actively forwarding at a time, not both of them or more than one. So currently there is no integration with CBAC and GLBP, the Gateway Load Balancing Protocol, which allows for active forwarding, which means that iOS Firewall is essentially just active standby. Now, we will look at later with zone-based firewall, there are some cases that you can do active forwarding. Now, essentially what CBAC HA does is going to be synchronizing the firewall sessions between the HSRP pair. One of the real key important points with this, though, is that it does not synchronize the router's configuration. So anything that is related to the control plane is not synchronized between the two of them. Now, this is different from how ASA's failover works, that you essentially do all your configuration changes on the active firewall, and then those are pushed down to the standby firewall when you write the config to standby. But in the case of the iOS firewall, it does not do this. It means that we need to make sure that our configurations are 100% synchronized on a one-to-one basis between them, otherwise that this feature is not going to work. Now, there are some other design limitations of this, one of the main ones being that asymmetric routing is not going to be supported. So we need to make sure that our outbound flows match our inbound flows, which we'll see is going to be a function of HSRP, and also that stateful failover is the only one that's supported. So it means that we have to synchronize the state information between the routers, where in the case of the ASA, you can choose whether you want to do just regular failover or do stateful failover. And the reason why you would not want to do stateful failover is that it's very platform intensive in order to replicate the state information. Now, additionally, when we look at the specifics of the documentation, you'll see that not all protocol inspections are actually supported for this. So in general, anything that is an application layer inspection, like a layer 7 policy map, a layer 7 class map, is not going to be supported for the stateful failover. Only basic standard layer 3, layer 4 policy maps are going to be supported for the failover. Now, the way that this works behind the scenes is basically that there are two different control plane protocols that we need to worry about in order for the inspection high availability to work. And the first, as I mentioned, is going to be HSRP. So HSRP is going to dictate which router is the active forwarder, which one is the standby forwarder for the firewall. Then there is also going to be a stateful switchover that uses a new protocol, which is the SCTP, not to be confused with STCP. And this is what is doing our state synchronization. Now, again, the important point about this is that it's not doing synchronization of the config. It's only doing synchronization of the state of the firewall. So when we look at the show IP inspect sessions, that session table is what is being transferred over the SCTP protocol. Now, from a documentation point of view, if we take a look at the, let's start at the main documentation page to be clear. We're going to go to Products, iOS, regular iOS, 15T, 15.2T, Configuration Guides, securing the data plane, content-based access control, and then the iOS firewall stateful failover. So this design is majorly different than the zone-based policy firewall. When we looked at most of the zone firewall to CBAC configs, they're pretty similar feature-wise, just there's a difference in syntax between IP inspect and zone firewall. But in the case of the high availability, there are different designs that zone firewall supports and CBAC doesn't. So make sure that you read through this document here, which is the iOS firewall stateful failover, and then under the zone-based policy firewall, which is the zone firewall policy high availability. So again, we will come back to this one in more detail after we go through the ASA. But if we look at, in brief, there's a diagram here that shows the logic of how this works. Basically, there's separate links that are used for synchronization of the zone firewall, similar to the monitor interface, the stateful failover link, and then the failover link in the case of the ASA. But for CBAC, we don't need these. It's going to be a very straightforward configuration that specifies just what is the interface that we're using the SCTP protocol on that's going to synchronize the state between the two of them. Okay, so again, this is under iOS firewall stateful failover. So I would recommend to read the first section of this, the information about it, so just what is the feature, what does it support. Then if we look at their configuration example, the main difference between this and a regular CBAC config is that we need to specify that there is an inter-process communication, an IPC, that goes between the two routers in the pair, the HSRP pair. So we say SCTP, this is going to be the local router, this is the remote router. Then basically make sure that they agree on this, like what's the port number that we're using on both sides. And then this is used for the inter-chassis redundancy. So redundancy inter-device, this name here is essentially the name that we're going to give to the HSRP group. So again, with these configuration guides, you don't need to know what are all the details of the syntax. You mainly just need to know what is the feature and what does it do. You can always use their examples to come up with a templated config and then change it around to match your particular individual design. Now, when we look at this from a logic point of view of just what's the overall pieces of the puzzle that need to go together, the first one is going to be just our normal CBAC config. So we need to make sure that CBAC is working in a non-high availability environment, that our inspections are correct, that the access lists are correct, that everything is working with the control plane and the data plane. Then we're going to configure HSRP, which is going to be to add the other router to the redundancy pair. Once HSRP is up, we configure the stateful switchover, which is going to be that inter-process communication between them in order to do the synchronization of the firewall. Then finally, we configure the high availability pair. Now we'll see that this feature is very highly subject to the order of operations, and most of the time in order to get it to work, you actually have to reboot the box. Now we'll see that when the failover actually occurs, it's kind of a strange way that they implemented it here, that when the active router goes into the standby state, in order to do resynchronization, the router actually just reboots itself. So a lot of the times if you're doing this config, you might have the configuration correct, but if it did not initialize in the correct order, it's not going to do so unless you actually reboot the router. So unfortunately, that's the normal case with this feature here, that rebooting is required in order to regain synchronization. We could optionally also configure what's the interval at which we do the synchronization between them. So essentially, how often do we copy the state table over? Then, of course, the difference is going to be if we copy it often, it's going to be more closely synchronized, but there's going to be more overhead in the control plane. Like it's going to take more CPU cycles to do so. Now, from a verification point of view, most everything is going to be the same in terms of HSRP, in terms of the regular iOS firewall. There are a couple commands here that are specific to the high availability. Mainly this one here, show IP inspect HA sessions. This is going to show the state table that should be synchronized between the HSRP pair. So if we look at the active router and look at its state table and then also look at this command on the standby router, if these two tables are different, then that means there's a problem in the stateful failover or the synchronization. On the standby device, if we don't see anything when we look at this output, then we know that the inter-process communication, the SSO, is not working between the two boxes. And usually the only way to fix that is to reboot the standby router. Okay, we can also clear the table if you clear IP inspect HA sessions. And the debug here, of course, is going to show the specific synchronization. When we create the state, it should show it being copied to the standby device. Now, in our particular case, this is what our topology now looks like. We're going to have router 1 and router 2 as the HSRP pair that is running HSRP on the inside network, and it is going to be running it on the outside network. Now, beyond the configuration of the regular firewall and the HSRP, there are some additional design considerations we need to take into account that are related to the routing domain. Now, as I mentioned, one of the limitations of this feature is that it does not support asymmetrical routing. So this means that the traffic flow that the packet leaves on, we need to make sure that it is the same flow that the packet is received back in on. So let's say, for example, that router 1 is the active router for the HSRP pair. So this means that when traffic comes from this test PC, and let's say that we're doing the web browsing to some server behind router 4. So the flow comes into router 3. Router 3 is going to send it to the virtual IP. Router 1 is the active forwarder, so the packet goes that way. Okay, 1 sends the packet out, and this is, let's assume this is the first portion of our TCP three-way handshake. This is the SYN. Now, when this session goes through router 1, it's going to be creating that entry in the state table. Here are basically the CBAC session. So it now knows I'm waiting for a SYN ACK to come back from that destination going back to my originating source. Now, if for some reason on the return flow, when router 4 returns the packet, if it goes to router 2, which should be the standby router, if router 1 is active, then 2 has to be the standby, this is going to be dropped as it comes in on this interface. And this is then what we consider an asymmetric flow. So if the packet is leaving in one direction and trying to return in the other, the iOS firewall high availability does not have any way to account for this. We'll see that in the ASA failover when we're doing active-active, and in the zone-based policy firewall failover active-active, there are some additional considerations that we can do asymmetrical routing. But the case with IP inspect plus HSRP, this is not supported. So this means that it's up to us from a routing point of view that we need to make sure that as the traffic leaves, it must be an identical path for the return flows. Now, the problem is with HSRP, it doesn't really cleanly interact with the rest of the control plane in order to allow us to do that. So let's say, for example, that we are using OSPF as our routing protocol. And we have an OSPF adjacency between router 1 and 3, 2 and 3, and 1 and 2. And let's say that router 1's address is .1, router 2's address is .2, and then the HSRP address is .254. This is our VIP, virtual IP. And we have some destination that we're trying to reach. Let's say it's router 4's loopback, which is 150.1.4.4. So this route is learned somehow from 4 to 1. Could be IGP, BGP, could be static routing, doesn't really matter. Okay, so the route is advertising in both directions. 1 sends a link state advertisement for this in OSPF, as does router 2. From router 3's perspective, what is its routing table then going to look like when we go to reach this destination over here? Is it going to say go to router 1, go to router 2, or go to the virtual IP address of HSRP? The problem is that there's no interaction between the IGP protocol and HSRP. So there's no way for us to change the next hop in IGP in order to try to redirect the traffic to the virtual IP address. So basically what we would see is that router 3 should have two equal cost multipaths, one equal route that goes to router 1, one equal route that goes to router 2. Then it's going to be load balancing the traffic based on whatever the Ceph flow data says. So like what's the layer 3 source destination, what's the layer 4 port source and destination, and it's going to get hashed in a kind of an equal distribution between the two next hops. The problem is though, when it goes to the standby forwarder and then goes out, the standby forwarder is not going to be able to create that state table information for the firewall. So the flow data or the flow would be able to go out, but on the return, it's going to have some problems because the firewall essentially is going to drop it. So we essentially now need to force the traffic to make sure that it lands on the virtual IP as opposed to the physical IP. And there's a limit to the ways that you can do this. You could do it with some sort of policy routing, you could do it with some sort of static routing, or you could do it with BGP. So in this particular design, I already have the routing pre-set up. We're going to verify how that design is working and how I solve the problem. In this case, it's with a combination of doing static routing and with doing BGP and modification of the next hop values. So let's go take a look at what happens in the what's happening right now in the command line. Okay, so on router 3, we are using EdgeRP in order to advertise our connected links to router 1 and router 2. So if we look back at the diagram, we're running EdgeRP on this interface here and this interface here. Okay, router 4, we're basically treating this like our ISP, so that's some remote destination. So this is the demarcation point of our IGP. Then we have, on the remote side, we have BGP. There's two different ASs. We have AS100 on this side, on the left, and then AS200, which is router 4. There's two different eBGP peerings that go from 1 to 4 and 2 to 4. So router 1 and router 2, these are the edge routers, and these are the ones that are going to be running the failover of the stateful firewall. So router 1 and router 2, they're advertising these internal networks to router 4. So the loopbacks are the routers, and then those LAN segments. So if we look at router 1 and we show IPBGP, we are originating advertisements for our own loopback and our other two internal routers, so router 2 and 3, and then we're learning router 4's loopback through eBGP. Now if we look at the specific configuration here, if we show run section router BGP, there is a policy that is applied to the eBGP neighbor, which is router 4 here. It says when I'm sending updates out to them, I'm going to send them through this route map for some sort of policy enforcement. And if we show run for the route map, it says when I advertise routes out to them, set the next hop to 136.1.124.254. And if we look at our diagram here, this address 124 is the subnet that is on the outside. And this .254, that's going to be the virtual IP that belongs to HSRP on the outside interface. Now basically the point of this is to make sure that when the return flow comes back in, that it always lands on whoever is the active forwarder for the firewall pair. Because the problem with the asymmetrical routing is that if the traffic leaves on the active forwarder outbound and it creates the outbound state, but then returns to the standby forwarder, it will not have the correct state and it's going to drop the packet. So it has to be symmetrical. This feature does not support asymmetric routing for the inbound versus the outbound flow. Now on the way outbound, there's a real easy way we can get this to land on the virtual IP. essentially router 3, if we show IP route, simply has a default route that points to the virtual IP. So in this design, we have two unrelated HSRP groups. We're going to have an HSRP config on the inside, and we're going to have an HSRP config on the outside. So the inside is to make sure that the outbound flows all get directed to the correct active router. Then the BGP policy, which is router 1 setting the traffic, or setting the update, I should say, to that next hop of the VIP. That's to make sure that the return flows come to the active forwarder. So on router 2, the configuration is identical here. If we show run section router BGP, we have the peering that goes to router 4. And it says, as I send updates out to them, set the next hop to be the HSRP address. From router 4's perspective, if we show run section router BGP, it has two different peerings. It has one to router 1 and one to router 2. Okay, there's a question here. Can we use the reverse path forwarding feature, the URPF? You could use that as an additional enforcement in the data plane, but it wouldn't fix the asymmetric routing problem. The only thing that URPF would do would be to drop packets that violate the symmetrical routing. So it would be an additional protection mechanism, but it's not a solution in order to fix asymmetrical routing. It's basically a solution to prevent the asymmetrical flows. So the way that we need to do this is to make sure that we're enforcing the outbound flow and the inbound flow to go through the same router. Okay, so let's look at the routing configuration currently. If we go to router 4 and simply show IP route, we should see that we're learning routes to the rest of the network through BGP. And this network here, 10.1.0.0, this is the one that the test PC is on. So the test PC specifically here is 10.1.0.100. So currently router 4 should be able to reach that. If we ping 10.1.0.100 and source the traffic from our loopback address, we need to make sure that we test this basic reachability before we move on to the firewall filtering. So let me get onto the virtual machine and let's see what its state looks like. So here this machine should be able to reach router 3, which is 10.1.0.3, which is on that particular interface there. 10.1.0.3. Then let's see if we can route through router 3. Let's ping 150.144, which we cannot. So actually what it is that I have the routing pointed to the HSRP, but I didn't yet configure the HSRP. So that's our next step. This is kind of outside the scope of the security, but unless you understand the routing design, then the whole solution is not going to work. So as I mentioned before, there's not a huge scope in just the general layer 2, layer 3 technologies that you need to configure in the scope of the CCIE Security Lab exam, but you do need to understand how this fits together. Otherwise, there's certain designs like this that won't really make sense why or how it's working that way. So let's go to our next step here before we then verify the full routing, is we need to configure HSRP. So there's going to be one HSRP configuration here, which is going to use the address 136.1.123.254. So this is the VIP for the inside. And then there's going to be another one here, .254, that is going to be for the outside. So on router 1, let's go to that interface, which is gig00.123. And we'll say standby 1. The IP address is 136.1.123.254. So for now, we're just going to start with the most basic config. Okay, same thing on router 2. Router 2 should have that on the same link. And then also on the outside. So on gig 00.124, there's another standby config that is for a different subnet. Now we can use the same group addresses here because they're on separate links. But just for clarity, I'm going to use two different numbers here. So when we do the verification, we know which particular groups they're referring to, inside or outside. So on gig 00124, we have the second group. Now again, for the symmetrical routing, we're going to need to make sure that the device that is active for the inside is also the device that is active for the outside. So we need to make sure that their priorities are equal, that the preemption configuration is configured properly, and that also we have some sort of object tracking to make sure that if the outside group goes from active to standby, that also the inside group goes from active to standby, and vice versa. So normally HSRP is not synchronized like this, that the configuration on one interface is completely independent of HSRP on another interface. But for this specific application, we need to manually make sure that these states are synchronized between the routers, that the inside you're active and outside you're active, or inside your standby and outside your standby. So if the design ends up to look like this, where we have active standby and then standby active, this will not work, because the traffic will leave in that direction and then return in this direction, and the routers will not be able to complete the state information in the firewall session table. So it has to be active at the top and standby at the bottom, or vice versa. Okay, so on router 1, it says that it is standby both for group 2 and for group 1. If we look at the show standby, it says that on group number 1, which is the inside, we're the standby router. Group number 2, we're also the standby router. And the reason why is that when the priorities are equal, they're going to fall back to the higher IP address as the tiebreaker. So router 2 has the higher IP address on both of these segments, so it's being elected active on both of them. So ultimately, when the flows leave the network and return, we need to make sure that they're going that way. Okay, so let's see from that VM, are we able to reach the destination now, which we are. So router 3 is sending the packets outbound statically to the VIP, so it's going to the .254. When the traffic is returning, 4 is sending it to the virtual IP based on that BGP config. So on router 4, if we look at the show IP route, the BGP routes are installed to the virtual IP. Now you'll see that there's a couple different designs that are supported for this. This one here is considered the inside LAN and outside LAN, where there's two different HSRP pairs, one on the inside, one on the outside. You don't necessarily have to set it up this way. Another supported design would look something like this. If we were to have so we have our PC on the inside that we're testing from. We have router 3 that is on the LAN segment of router 1 and 2. So this is the active standby pair. They could go then to separate WAN links like ISP-A and ISP-B. Now in this particular design, it's a lot easier to maintain the symmetrical routing simply by doing network address translation. So let's say, for example, that router 1 is elected the active router, and when its flows are going outbound, it's doing a network address translation to this IP address. As long as whatever this IP is not being advertised in that direction to ISP-B, then it always implies that when the traffic leaves that way, it's always going to come back in that way. But in our case, it's a little bit more complicated because we have the inside and the outside LAN segment. So we always need to make sure that when the traffic leaves from 2, it has to come back from 2. And you'll see when we look at this in the documentation, this is what they call the what do they call this? It may be in the zone firewall config, where it calls the, it says the WAN-LAN topology or the LAN-LAN topology. So in a WAN-LAN topology, 2 devices connect through LAN interfaces on the inside and then WAN interfaces on the outside. There's no control on the routing of return traffic received through the WAN links. WAN links can be provided by the same provider or different providers. In most cases, it's different service providers for redundancy. In the LAN-to-LAN topology, this is what we have. So we have an HSRP pair on the inside and an HSRP pair on the outside. Okay, so we have the first step then, which, if we go back to our order of operations, which was actually our second step, which was the HSRP. Okay, so HSRP is working. Next thing we're going to do is configure our firewall rules. So on router 1, we're going to configure an inspection policy. IP inspect will say the name is CBAC HA. And we want to do just basic inspection. Let's say TCP, UDP, and ICMP. Now again, one of the key points about this feature, the iOS high availability, is that it does not synchronize the configuration between the 2 routers. So this inspection policy that we are defining on router 1, we need to make sure to identically define it on router 2 exactly. Now also, if you look at the documentation in the release notes for this, it does also specify what are the other hardware requirements, like the restrictions. It says that the active and standby devices must run identical versions of iOS, and they must be connected, okay, they have to be connected to the switch, that's self-explanatory. But also there are some other hardware type requirements where basically in this case, if we show version include iOS, these 2 are identical platforms. This is essentially the only case that you would want to run it. So just like in ASA, if you have a 5510 and a 5520, they cannot be in the same failover pair because it's different hardware. Or if you're running 8.2 on one and 8.3 on the other one, it's not going to be supported. So when you test this out, make sure that you pick 2 routers that are identical. If one's a 2800 and one's a 2900, you're probably going to have some problems because they have different versions of software and then, of course, different hardware capabilities. So again, from a configuration point of view, any change I make on router 1, I need to make sure to identically make it on router 2. Okay, so we have the inspection policy, that's TCP, UDP, and ICMP. Then we're going to apply this outbound on the links towards router 4. So we're doing the inspection as traffic leaves in that direction. Now we know from the other CBAC configs that we also then need a return ACL. So the ACL is going to do our explicit exceptions like permit BGP control plane, and then it's also going to deal with our denies. So we're inspecting out, and then we have the ACL in the reverse direction inbound. So on router 2, let's specify that we have an access list outside in, IP access list extended outside in, and let's simply say deny IP any log. And then those logs are going to tell us what we need to explicitly permit in the control plane. Then on that interface, gig 00124, let's say IP inspect CBAC HA we're inspecting out, and IP access group outside in, inbound. Okay, router 1 is going to need to do the identical thing. So it's going to have the access list that says deny IP any log. And technically, it doesn't need to be a one-to-one correlation between them. There can be differences in the configuration, but it doesn't make sense to do it that way, because otherwise you could have traffic leaving on one policy, and then when you fail over, it fails over to a different policy. So you would manually want to make sure that the configurations are synchronized. But the main point being, it's not like how ASA works, or it's not like how Nexus 5K works, where you can manually, or you can automatically synchronize the configs between the failover pair. Okay, so we have the access list, and then at the link level, do show run interface gig 00124. We have the inspection out, and then the access list returning 124. Okay, now we saw there on router 2 we had some log messages. One of them here, it says it's denying UDP coming from router 2 going to 224.0.0.2, which is what here? This is our HSRP control plane between them. So if we look at the show standby, we'll see that on both routers, they both say that they are active. This is because the HSRP is getting filtered. So those local hellos from HSRP, those are not being inspected. This means when we show run section access list, we need to be more specific here. We need to say to permit UDP, and we could say the remote neighbor if we wanted to put their IP address. But in general, if we wanted any HSRP, it would be to permit UDP any to 224.0.0.2, which is the all routers multicast, and equal to, I want to say 1985. But let's double check that. Yeah, 1985. If we did a debug IP packet, we would see what the product or what the port is. If we debug IP packet detail, we should be able to see 224.0.0.2 UDP 1985, which it is. Okay, but that's the HSRP exchange. When we show access list, we also are going to need to account for the BGP flows. So you can see when I did that debug here, debug IP packet, when you send this to the console, it's very likely that you're going to overrun the console buffer and then possibly lock yourself out of the CLI. So when you do this, you always want to make sure to send it to the buffer. So to do that specifically in global config, we would say logging console at level 6 or below, logging buffered at level 7, then set the buffer to some larger value, like let's say 100,000 bytes. Then when we show log, the debug messages would show up here, but they wouldn't go to the console because the console is doing informational where the buffer is doing debugging. Okay, we can see the other packets that are getting denied here are TCP 179 from router 4. So that's the BGP peering. So we need to make sure also for IP access list extended outside in, permit TCP any equal to BGP, and permit TCP any equal to BGP any. Because we don't necessarily know which direction the BGP session is. We don't know who's the client, who's the server. But again, we need to make sure we have this identical configuration on router 2 as well. So let's say show run section access list. And we need to copy and paste this onto router 2. So on router 2, let's say no IP access list extended outside in, and then paste the other list. So we can see the BGP peering is up. And if we show standby, let's say show standby pipe includes state, we need to make sure that they both agree, let's say state or group. We need to make sure that they are active and standby. Again, if we have one that is active on the inside, standby on the outside, and the other one that is standby or active on the inside, standby on the outside, then there's going to be a problem with the asymmetrical flows. So whichever router is doing the active forwarding, it has to be doing it actively on both inside and outside at the same time. Again, assuming you're doing that double-sided LAN design, which is what we have here. Okay, so let's actually try out the inspection. So let's go to our virtual machine, and let's go ahead and send some traffic through. So let's telnet to router 4. We can see the connection is working. If we look at router 1 and show IP inspect sessions, we see router 1 doesn't have any state data. If we do the same thing on router 2 should know about that telnet session, which it does. So we can see that by default, just with HSRP, that doesn't mean that the firewall is going to be stateful. So they're not exchanging the state information for the session table. This is going to be what our next step is to configure the SSO. That's the control plane protocol that synchronizes the state table between them. Okay, but we know that the CBAC itself is working, the inspection is fine, and we know that HSRP is fine, that we're both active on the inside and outside on one of the routers. Okay, so next let's look back at the documentation, and let's not go step by step through their example. Now, of course, when you're reading through this, you want to first go to the how to configure, and then read through, step by step what they tell you to do. In this case, I'm just going to look at their example, and then we're going to work backwards from there. So configuration example. The next portion is this redundancy config, and then the IPC config. So this is to do the actual synchronization between them. Now notice here that under this redundancy for inter-device, it says the scheme is the standby group named HA-in. So this means that on our interface, here they're saying that this is the interface inside. We need to give this a name. So I'm going to say that this is our stateful CBAC or CBAC HA. Okay, so let's go to router 2 and let's show run interface gig 00.123. This is our inside interface. And standby 1's name is, we'll say CBAC HA. Okay, if we show standby, we can see this group name now is CBAC_HA. If you don't give it a name, you can see that it chooses this default one that's based on the interface naming. But just from clarity, the configuration point of view, you probably want to give it a name because that's what we need to reference under the redundancy between the two chassis that we're trying to set up. Okay, so same config identically that we want to do on the other side. So you'll see in their example they have other things you don't necessarily need to change, like they're making the timers lower, they're lowering the priority, they're doing preemption, they're doing the tracking. The tracking we'll come back and talk about in a minute once we actually test this out and see what the result of it is. But at a minimum, we just need the IP address and then the name. And technically, you don't even need the name because it has one by default. But let's say the same thing on router 1 as well. gig 00123. Okay, next we're going to do the, if we go back to their example, we need to do the redundancy inter-device, and then we need to specify this IPC zone. So this here basically is just going to specify their IP addresses, where in our particular case, from router 1, the address is 136.1.123.1, and the remote IP is 136.1.123.2. Okay, the other portion of this is to say redundancy inter-device, and the scheme, I called it CBAC underscore HA, I believe. CBAC underscore HA. So that is router 1 side, and then the other side we need to flip these around. Now what we should see if this is working is that they start to synchronize the information about the state table. So the final verification of this is ultimately going to be from the application level. That from the virtual machine we have the telnet session going through the HA pair, will fail the active one, and we should see that the telnet session is going to remain up because that state information gets transferred over to the standby one. But before we test the final result, we probably want to make sure that they form the adjacency here for the inter-process communication. And this was, as I mentioned in these verification commands, if we show IP inspect HA sessions, this is going to show the state table. But before we get to the state table, we want to look at the show redundancy inter-device and the show redundancy state. Notice what it says here is that we're pending standby, but it's not going to actually take an effect until we reload. And right now communication is down, which is bad. So on this box we actually need to save the config and reload. If we look at the same thing on router 2, show redundancy inter-device and show redundancy state, it says that my state is active, where previously on router 1 it said that its state was, basically the pending state was standby. So let's see, once router 1 is done with the booting, it should detect that it is going to be the standby state. There's a question, this is a 15x code feature only. I think it's in the late releases of 12.4T. Let's look at the doc here. At the bottom it should say, it says it's in 12.4T. I've never done it in this version. I've only done it in the 15s. But I think as long as the code is identical between the pair, then it should be fine. But you wouldn't want to run one of them as 15 and then one of them as 12.4T, because they may not support the, unless there's exact feature parity, they're not going to understand the synchronization between the two of them. Okay, so now that router 1 is booted again, it is actually rebooting itself again. So now that it has joined the pair, it's doing a self-reload, reloading self per request of the peer. Basically, it joined the inter-process communication and router 2 is now saying to 100% synchronize, you need to reboot. So it's actually rebooting twice. But at least if you get to this point, you know that the feature is working, because the other router is telling them to do the reboot in order to do the, here, this is for the inter-device redundancy. Okay, so now that one has booted again, basically what we're waiting for is for it to join the HSRP group. So if we look at the show standby, right now it should be in the listen state because it's initializing the process. Then once we look at the show redundancy inter-device, or the show redundancy status, or actually state, show redundancy states, it says my state is hot standby. This is what we're looking for. And the communication is up. If we look at the same thing on the other side on router 2, it should say that it is active. My state is active. The pure state is hot standby. Okay, so now let's look at this from the actual synchronization of the firewall. If we look at the show IP inspect HA sessions on both of these, right now we don't have any inspection that's going on in the data plane for the firewall. So let's go to our virtual machine that's behind the firewall, and let's say we do a telnet to router 4. And let's generate some traffic. Let's say show tech support, for example. If we go back to router 2, who is the active forwarder, we should see that the state is listed here in show IP inspect HA sessions. Let's show IP inspect sessions on router 2. It does have the regular session, but it's not in the HA. Actually, there's one thing that I missed. I forgot to turn on the redundancy for the inspection group. So by default, CBAC, even though if you have the inter-process communication, it doesn't turn it on for that particular inspection. So if we look at their example, there's another command which is redundancy at the end of the inspect command. So at the link level on router 1, if we show run interface gig 00.124, we need to say that this inspection list is tied to the redundancy pair. And the stateful redundancy pair is CBAC_HA. And hopefully I don't need to reboot again after I change this. Okay, so let's exit that session. Let's create another one and see if router 2 generates the state for that. So show IP inspect HA sessions. Now we do. Okay, it says in the high availability pair, I am the active forwarder. If we look at this on router 1, it should say that it is not the active forwarder, it's standby. So it knows about the state. It knows that the VM telnetted to router 4. We can see destination port 23. But the flow information, the actual data plane is going through router 2. Now I mentioned this before, there's kind of a strange result with this feature, that if the active router loses its active status, in order to synchronize, the way they do this is simply to reboot the box. So this means that if we were to go to, and let's take a look at our particular diagram here. If we were to go to the switch that's attached to router 2, where specifically these links, they go to switch 1, port 2. And if we were to shut this interface down, it's actually going to cause router 2 to reload, because it goes from the active state to the standby state. Okay, there's a question here. Does the SCTP duplicate similar protocols like in the ASA, like IKE, UDP, HTTP? We'll see that the stateful configuration of IPsec is different than the CBAC. So there is a way to do stateful replication for the other protocols, but it doesn't do this by default. If you look at the doc here, it tells you specifically what is synchronized. And it says here, it says in this document, so it might be the zone firewall one that specifies what is actually synchronized. Here it is. Currently, only layer 4 TCP and UDP protocol failover supported. Therefore, all TCP-only sessions, UDP-only sessions, and single-channel granular protocols for which L7 inspection is not supported are failed over. So, like your web inspection, then it's not going to synchronize that state if you're doing some sort of complicated application-level inspection. So in our case, we're just saying inspect TCP, UDP, that state will be replicated, but the ICMP pings won't. Or if we do like IP phone calls, that's not going to be synchronized because that's a layer 7 inspection. So it's very, very, very basic things that it is synchronizing over. Okay, so let's go to the switch now. Here's switch 1. And if we show CDP neighbors, router 2 is on this port here, fast Ethernet 102. Let's shut down that link. And we can see now router 2 reloads. 1 should promote itself to the active state. And from the VM, this session should still stay up, which it is. Oops, and actually just close that window. Let me go back to it. But if we show IP interface brief, we can see that the telnet session did not get disconnected because it was stateful. But again, it's kind of an odd feature because if there's now a failure in the control plane, like here, the link flapped, it causes the router to reboot. Or if there's some sort of problem with the HSRP synchronization, like if both of them become, or both of them go to standby, then the router is going to reboot. So it's, whether you would actually run this, I've never seen it implemented in production. Most of the time, anybody who wants to do this is going to do this on an ASA pair or other boxes that are not the routers. But technically, it is a supported feature if you wanted to go that way with it. Okay, but let's recap the configuration again here in summary. If we look at show run on router 1, we have, first off, we have the regular CBAC inspection. Okay, so this is whatever our inspection rule is. And for the outbound rule, we then have return inbound ACL. So this says make sure to permit the control plane. This is HSRP. and then whatever our routing protocols are. In this case, we're using BGP on the outside. Traffic is leaving the network. We're inspecting it. And then we're going to call this stateful group, which is the HSRP pair of the inside. Okay, the HSRP pair on the inside is then tied to the inter-device redundancy. And specifically, what is the inter-device is controlled by this inter-process communication, the IPC zone. So we're saying that the protocol is SCTP. These are the port numbers, and these are arbitrary. You could change these whatever you want as long as it matches on both sides. And then we need to say no shutdown. So when router 2 comes back and it's fully loaded, if we look at the show IPC SCTP statistics, we could see that we have that guy configured. If we look at show IPC session all, now which one is it here? Not session. There's one of these that shows the adjacency. I think if we just say show redundancy inter-chassis though, or not inter-chassis, inter-device. And show redundancy states. So it's still not fully synchronized. But again, this should say, one of them should say active, and then the other one is HA standby or hot standby. And then when we look at the show IP inspect HA sessions, ultimately that is telling us, is the state information synchronized between the two devices. But remember that behind the scenes, you need to make sure to solve this routing problem to begin with. So the way that I did this outbound was just to point a static default route to the VIP to make sure that the return flow landed on the virtual IP. In the BGP peering between 1 to 4 and 2 to 4, I had that route map that's manually saying change the next hop to that particular value, because otherwise the routing information normally points at the next hop of the physical link.